right, so let's look at some more geometric terms. We're getting near the end here. So we're going to be talking about some two-dimensional geometric terms, and the first one is a polygon. Right, so for your definition, I'd like you to write in the red words. Polygon is a closed figure that is the union of line segments in a plane, and that polygons have 3 or more sides. Polygons are named by the number of sides they have, and we're going to look at some polygons. Now, you don't have to write down every polygon. We'll talk about certain ones, and they'll stick in your head. Right? So, but for right now, I'd like you to know what a polygon is, and then we're gonna look at some things about some polygons. So, a polygon is a finite portion of a plane. Right? So, when we were looking back here at our rectangular prism, if those lines go on and on forever, right, then I have a plane. If I stop those lines and we just look at a finite portion, we have a polygon. And usually we're looking at, we have a figure here, a geometric figure, we're looking at just a finite portion, and so those lines would end. Let's go back to polygon now. Right, so a polygon extends in 2 directions, so they have length and width, but because they're finite, they can be measured. We can't measure a plane. You can't measure infinite. What's infinite? Right? But we can measure something that's finite. In your notes, I don't have a diagram or a naming for the polygons, but you can jot down some things from the next slide. Now, certainly you don't have to write all of this down, and you can even wait, because if you notice, there's some red words that say class discussion. So this is one of the pages that I want to discuss with you as a class. Right? But I want you to kind of take a look. I'm just going to go over a couple things. Right? So we have some different polygons here, and polygons are named by their sides. So if a polygon has 3 sides, well, it's a triangle. Not only does a triangle have 3 sides, it has 3 angles, 3 vertices, no diagonals, and you can make one triangle out of a triangle. That seems to make sense, right? It's a triangle. Now, what does that mean? So when I say number of triangles, by the way, I mean, yeah, if you do this, you'd have, should draw blue on blue. Right? No blue on blue. How about yellow on blue? Yeah, if I did this, I'd have 2 triangles. But that's not what I'm referring to. I'm referring to the number of triangles you can create with a diagonal. Now, you might say, what's a diagonal? Right, so let's talk about a diagonal. Right? So a diagonal goes from one vertex to a non-adjacent vertex. In other words, a vertex that is not next to. Right? So where I draw the green dot, right, what is it with me drawing the same? Can't draw green on green either. Although I think it looks kind of brown. So that would be adjacent. That would be an adjacent vertex to this one. Right? So we're talking about one that's not adjacent. Right? So I can't draw any diagonals in the triangle because whatever vertex I'm looking at, so if I'm looking at this vertex, both other vertices are adjacent. Right? So there is no non-adjacent vertice, so I can't draw a diagonal. Right? So I can't create any triangle. I can only have one triangle here, right? Because I can't draw any diagonals, so I can't make any more. The quadrilateral has 4 sides, 4 angles, 4 vertices, 2 diagonals, and you can create 2 triangles. And so those 2 triangles have to be from from all the diagonals you can make from a single point. Right? So that's all the diagonals I can make from a single point. So I can make 2 triangles. That's not all the diagonals there are, however, because we have 2 more non-adjacent vertices, so I can draw in another diagonal. Right? So it has 2 diagonals, but it only creates 2 triangles because we're talking about the number of triangles from all the diagonals from a single point. Let's look at the pentagon here. Right? So from one vertice, I can draw 2 diagonals. So that, I should say one vertex. Vertices is plural. From one vertex, I can draw 2 diagonals. From those 2 diagonals, I can make 3 triangles. However, there's actually 5 diagonals, altogether, because there's another diagonal here. there's another diagonal here, and there's another diagonal here. Right? So there's 5 diagonals, but I can make 3 triangles with all the diagonals from a single vertex. The hexagon from a single vertex, 1, 2, 3, I can make 4 triangles, but there's 9 diagonals altogether. So we have another one here, and all you got to do is look for one non-adjacent vertices that you haven't intersected. It's like, for instance, here and here. And let's see, I'm missing that one, got that one, I got that one. I don't have this one. There we go. I don't have them all. I don't have this one here. And I feel like I'm missing one. I didn't count as I was going along, and I should have. Got 1, 2, 3, 4, 5, 6. So maybe I got them all. I'm just drawing it. I think I guess I have the, oh, no, I don't. No, I don't. No, I draw that one. Yeah, I guess I do have them all. That one diagonal, the one that goes from this point here to this point here, is kind of crooked. So it's kind of throwing me off. But there are 9 diagonals. Kind of sloppily drawn in that one. All right, so after a while, though, it gets really, really crowded trying to draw diagonals. Right, so I'm just going to draw all the diagonals from a single point so you can see the triangles. Heptagon has, actually, it's a heptagon or a septagon. 2 different names. It's a 7-sided figure. One is Greek, one is Roman. I believe the Greek is the heptagon and the Roman is the septagon. Right? Either is fine. It has 2 names. Has 7 sides, 7 angles, 7 vertices, 14 diagonals, and I can draw 1, 2, 3, 4 diagonals from a single point, which creates 5 triangles. Octagon, 8 sides, 8 angles, 8 vertices, 20 diagonals. I'm going to be really crowded if I draw all those in. And I can create 6 triangles with the diagonals from a single point. This may be the last one I do, because you can see my pen's kind of thick. So it's getting a little crowded in these triangles there. So we have 1, you can't see if I point, huh? But I have 5 diagonals there, right? So I have to have 1, 2, 3, 4, 5, 6 triangles, right? I have one more triangle than I have diagonal from that single point. The nonagon, 9 sides, 9 angles, 9 vertices, 27 diagonals, and you can create 7 triangles with the diagonals from a single point. I think I'll stop drawing now. The decagon, 10 sides, 10 angles, 10 vertices, 35 diagonals. There are 8 triangles that we can create from a single point. And the dodecagon, 12 sides, 12 angles, 12 vertices, 54 diagonals. The whole figure would be covered. That almost looks like a circle, doesn't it? Because of the size of it and how many sides there are. And we can create 10 triangles from the diagonals from a single point, from a single vertex. Now, sometimes we just don't give names to certain polygons. For instance, the 11-sided polygon, it doesn't really have a name. You know, it might be kind of an obscure name that nobody uses. So if you don't have a name, you get called an n-gon, where n's the number of sides. So you have 11 sides, you're an 11-gon. You have 13 sides, you're a 13-gon. And so some of them, they just don't get their own names. But we have n-gon here. And n's going to refer to the number of sides. N is also the number of vertices and the number of angles. I wonder what the number of diagonals and triangles would be. Now, since n is a variable, we're not going to have a number answer for diagonals and number of triangles. We're going to have some kind of formula. But I want to take a look at, pause the tape, look as long as you like, and see if you see any patterns that might help you figure out what the formula for the diagonals and the number of triangles might be. And even if you don't figure those out, do you see any patterns at all? Anything at all you notice in the number of sides, angles, vertices, diagonals, and number of triangles? And we'll talk about that in class. All right, so I'm going to move on from this page, and I'm not going to answer any more, and we'll do the rest in class. Right, so some polygons are what we call regular polygons. Right? So we're going to talk about those. In your notes, before you see the word regular polygon, you have 2 other vocabulary words that we're going to talk about first before we can even talk about regular polygons. And those are equilateral and equiangular. Right? So next to the words equilateral in your notes, underneath it, just put that doesn't have dimensions, don't apply. Equilateral, and I'm thinking of regular polygon. Equilateral and equiangular as a description. You're not going to be writing any dimensions there. So a polygon is equilateral if its sides are all the same length. All right, so for the definition, for equilateral, just put in sides are the same length. Next to the vocabulary, and there's no naming, no diagram. But we may write something in there in a moment. So equiangular means all of the angles are the same measure. Now, some polygons that are equilateral are equiangular, and some polygons that are equiangular are equilateral, but sometimes they're not. A regular polygon is a polygon that's both equilateral, so all sides are congruent. That little symbol there with an equals with a squiggle, that means congruent. And equiangular, all angles are congruent. In your notes under regular polygon, I'd like you to write for the definition, polygon that's both equilateral and equiangular. And under equilateral, you can write all sides congruent. And under equiangular, you can just abbreviate there, angles are congruent. For a number of dimensions, that would be 2 dimensions. All polygons are 2 dimensions. For the diagram, this happens to be a regular pentagon. I could have drawn a regular hexagon or a regular triangle or a regular quadrilateral or anything else. But I just chose a regular pentagon. It's good enough. Right? And when you see a figure that has the same number of those little lines there, they're called hash marks. So if you have 2 sides and they have the same number of hash marks, that means they're congruent. So this means that, so with your diagram, actually you could put this under the naming portion. So AE is congruent, and that would be line segment. AE is congruent to ED. So this is for naming. Is congruent to DC. Is congruent to line segment CB. Is congruent to line segment AB. So you can add this portion for this part for naming. And then you can also add in this part. Angle A is congruent to angle B, is congruent to angle C, is congruent to angle D, and we'll have to write underneath, is congruent to angle E. At least I have to. All right, so under the naming symbol, you can add that next to your diagram. Let's put this part in, let's write in green. Let's put this part here next to the naming and under naming and symbols for equiangular and equilateral. All right, so I guess we'll do the equilateral one, which is the second one there. So in that box there for diagram and naming symbol for equilateral, I want you to write an equilateral and you can abbreviate quadrilateral, just put quad, that is not regular. So in other words, it's a quadrilateral. All the sides are the same length, but all the angles aren't the same length. And remember, quadrilateral has 4 sides. Can you think of what it is? Pause the tape if you want to. See if you can come up with the answer before I write it down there. And then you can let me know in class if you figured it out. All right, so the equilateral quadrilateral that's not regular is the rhombus. Right? The rhombus has all sides congruent, but its angles aren't congruent. In the box that said the box for diagram naming for equiangular, I want you to write in equiangular quadrilateral that's not regular. And you can abbreviate quadrilateral and just put quad. Right? So a 4-sided figure that has all the angles are congruent, but it's not regular. Means all sides aren't congruent. So before I write it down, if you want, you can pause the tape. think of what that answer is. What could that polygon be? That quadrilateral. The quadrilateral is a type of polygon, but this is very specific. It's got to have 4 sides. So what is it? It is, did you figure it out? Pause tape if you need to. Did you say rectangle? All the angles are 90 degrees, but the sides don't have to be congruent. Now, do you know the regular quadrilateral? In other words, all the sides and all the angles are congruent. Such a common figure. Probably any second grader knows this figure, but do they know it's a regular quadrilateral? Probably not. You know what it is? It is the square. So you can let me know in class how many of those 3 you figured out. So in your notes, just put that in those parts in there. You can squeeze it in under the equilateral and equiangular. And if you want, you can put regular quadrilateral for space. You can put next to regular polygon, or on the side of the paper if you can't find any more space, or a little sticky note. All right, so before I move on to circle, I'm going to pause this tape, right, and I'll come back with circle. Bye for now.